So we'll try to talk about structural and electronic aspects of perovskite for solar cells. We've been spending a couple of years now monitoring this field and trying to contribute. And there are two important conclusions that we can draw. That is, stick to the lead. You can try to make it with other metals, but it doesn't really work, or it's too difficult, or they don't get high efficiencies. And the other thing is get rid of the metal ammonium. So the metal ammonium component, that is intrinsically labile. It gives problems. We stick with lead and we try to focus on formamidinium. But if you take this formamidinium lead tri-iodide, so that is the formamidinium is just an NH2, a CH, and another NH2. So that's the organic cation. But if you make that material, and last year there was a first-year course, first-year student, they made this formamidinium lead tri-iodide, this black material. So they were able to grow crystals with a high temperature method. But if you leave these crystals for a couple of weeks like that, then they turn yellow. So they turn into the delta phase. The black material converts directly to the yellow material without losing the crystal form. I mean, you can have a crystal which is black, and a few weeks later it's yellow. So the internal crystal structure changes, but the crystal itself, the shape of the crystal does not change. So that's not what you want. You want it to remain black, and you want to have formamidinium lead tri-iodide. That is the most interesting material. We don't want metal ammonium lead tri-iodide. We try to get rid of it. But we focus on the formamidinium, and we want to have the high temperature alpha phase. So if you make it at high temperature, then it's black. But if you leave it at room temperature, after a few days, a few weeks, it turns yellow. But if you would heat it again, you can get to the other phase again. The alpha phase is depicted here. It's a very nice cubic packing. All the components are exactly in a cubic lattice, as you hope, like ideal. There's these octahedra, they're formed by the halogen. And the delta phase, so the yellow phase here, you see that if you look at the sides, then the connection between these octahedra is lost. So it is as if these octahedra, they move in the crystal, and thereby the conjugation is lost. So there's no more interaction with the next layer. So that makes it yellow. So this is the yellow delta phase, and we want the black alpha phase. And there are also other phases possible, but this shows the change of the structure, what you want to control, basically. The other one, around the operation temperature, it changes phase. So you don't want to have a solar cell that changes crystal structure while it's in operation and cooling down. Below the video, there's some information on people that also say that we should get rid of metal ammonium. A lecture from Gretzel, so Michael Gretzel, he's one of the big people in the solar cell field, dye-sensitized solar cell, but also perovskites. So he states we should get rid of it. There's a peer review from René Janssen. René Janssen is in Eindhoven. He's also working very intensively on perovskite solar cells. It's widely accepted that Ma-based perovskites are less stable. And here's also some papers from other groups that also state that is the component we should get rid of. But still, latest papers, metal ammonium is still there for a few percent, for like 5%. This is the black alpha phase. This is another view of the yellow delta phase. People are also trying to incorporate cesium lead tri-iodide to control the structure, but this is the structural effect that you see in the perovskite. We want to have the black alpha phase. And one thing that we can try to do is by using doping. Zinc doping can influence this. And recently also formate doping. So using a few percent formic acid type anion that can change the phase diagram. One of the most recent papers from Gretzel, it contains formate anions. So instead of the iodo at the edge, putting formate there, maybe only on the outside, that can influence the stability at room temperature or the phase diagram. Another thing that we want to get over, you need a layer of this photoactive nanomaterial. That's a very good, promising solar cell material, but you need to have all the octahedra intact. So here you see a visualization of such a layer, and you see that it's not just this unit, but it is a layer of this unit in all directions, and all the octahedra are intact within this layer. And that causes conjugation between the units. So one unit, it's not black. You need several, and actually you can wonder how many you need to get really the good band gap. So we go from a nice cubic material. This is in this case cesium lead bromide. So here we see the cesium in the middle. We have a nice cube, and we have these octahedra around it. That is the basis for these types of materials. But you can also look at it from a different perspective to the crystal. Now, this is one of these octahedral coordinations around the lead. Here we see the formamidinium ion or the cesium ion. And so here you see another view of the same material. Here you see that all the octahedra are together. So this is an intact octahedra that can basically conjugate with all the positive charges from formamidinium around it. Now, the main electronic properties, they actually come from the lead and the iodo. The formamidinium or the methylmonium or the cesium, it has a role, but it's not really the color or the conjugation. If you try to look at these structures and you, for instance, get file, if you want to build a perovskite lattice, then actually this is part of the unit cell. So it's just PBBr3. Of course, there's also the other ion. But so if you start building a lattice, you just multiply this unit in all directions, and then you get here. Now, what is strange about this picture here? If you look closely at this picture, then you see that at this side, and at this side, and at this side, there are all these octahedra. They are forming the end of the crystal. But on the other side, there's actually the lead ions on top. So these three sides of the crystal, as it is drawn here, have a different outside than the other ones. That's not what you want. You want to have intact octahedra. Otherwise, you have dangling bonds. Does anybody know what a dangling bond is? If I take a diamond, maybe somebody has a diamond ring here. So if I put my finger over the surface of a diamond, what do I touch? What is a diamond made of? Carbon. So a diamond is made of carbon. But if I put my finger over a diamond, do I touch carbon atoms? No. What do I touch? If you take a diamond lattice, of course, it's carbon with tetrahedral coordination, and it's like an infinite lattice. But if you take a look at the surface, then the carbon has at least one free valence. This would be a free radical on the surface, but that's not going to happen. Of course, it's going to react. If you split a diamond, you crack it open, then if you do it in high vacuum, you may get a surface that consists of these radicals. But as soon as you put in, well, anything, it will react. You're basically touching a monoatomic layer of hydrogen atoms. If you put chlorine gas there, you could make chloro-terminated diamond. But these dangling bonds, so this is what you call a dangling bond. So it's a free valence, and it doesn't like its situation, so it's going to react. And so for diamonds, it's very likely to be a hydrogen atom. For graphite, it's the same. If you have graphite are just hexagonal benzene type rings, they're all conjugated, but on the outside, there's not carbon, there's termination by hydrogen or hydroxy or another group. So here you have the same effect. On this side, the lead ions, they don't like the situation, so they will somehow react. Or if you want to build a perovskite lattice, you have to take away some of these layers there so that you get into a situation where you have all the octahedra intact. So you cannot make a proper perovskite structure just by taking the CIF file or the unit cell. You will get something that is like an infinite crystal, but if you want to make a finite crystal, it doesn't work. If you have a vacancy like that on the surface, it can maybe coordinate with pyridine or with another ligand. But this is a structural effect of these perovskites. The black is the lead, the purple is the iodine. You see here the formamidinium. So this is a crystal that's built up from the CIF file, but you see that at all sides we have the octahedra intact. So just like the picture I showed before, this is what you need to get the proper material. This is actually from a recent chemical review. So here you see the crystal packing of the perovskite unit. Now, if you want to make a layer, you need all these units packed together, forming a layer. And here you see like the visualization of the crystal. So they're little crystals packed together, but they all have this perovskite structure, and they all should have intact octahedra. Because if they don't have that, then you actually have a defect. And defects, they cause loss of charge. So the next thing is orbitals. All the people in the class, they know that going from high school to the university, one step you have to make is to go to orbitals. Maybe you still have the view in your head, the Bohr model, that an atom is like a nucleus with an electron that's circling in an orbit. And that is the picture that you have of an electron in an atom. If you go study chemistry, then you will learn about orbitals. So an orbital, can you tell me what an orbital is? Orbitals, that is something you have to learn about, have to get acquainted with. Of course, it all comes from quantum chemistry, molecular orbital theory, that is important. And it is like a cloud of which the density becomes less if you go far away. So these things here, these colorful pictures, they depict the orbitals of such a perovskite material. Even for chemists like us, these ones are pretty weird. We will get to that, but this is the picture. So you have the same lattice, but you have the orbitals drawn into it. And this is the, okay, we can call it, in chemical terms, we can call it the highest occupied molecular orbital, the HOMO. But in physics, we call it the valence band maximum. A semiconductor has two bands, a valence band and a conduction band, the low state and the high state. The conduction band maximum is, well, visualized by these orbitals. Can you see anything strange about these orbitals? Especially on the right. Is there something uncommon about them? Especially about this one. If you look at this orbital, and it is the HOMO. It's the highest occupied molecular orbital. Doesn't it look weird? And why? And what looks weird on it? What do the colors mean in this picture? Exactly. So this is an s orbital. This is S. It is isotropic, so it is the same in all directions for the 1s. This is the p orbital. So here there's a node. There's no electron density in this plane, but there's also a mathematical change of the sign. This one has a plus sign, this has a minus sign, mathematically. It's not that the electron is different, but it's just the electron cloud has two sides. It goes from blue to red to blue to red to blue. So it has, as Milton is saying, it has anti-bonding character. So it is the highest orbital. It's the valence band maximum. It's like the HOMO, but it has anti-bonding character. In that way, you have these structures, you have these intact octahedra, you have a layer, but you also have the orbitals of this material. The funny thing is that the valence band maximum, so the highest occupied molecular orbital, in which there are electrons, it has anti-bonding character. This is made with periodic boundary conditions. So basically, these calculations, they were performed on, let's say, infinite crystals. We have this unit, and it repeats as far as we go. This picture, it is basically composed of the 6s orbital of the lead. So that's here, for instance. So it's like that one here. It's an s orbital, but it's coupled to the 5p, a thing like that, of the iodo. So this is mainly the lead and the iodo. They are important for the band gap, for the color of the material. The formamidinium or the cesium or the metal ammonium, it does not play a role in the orbit. This is the p orbital on the iodo. So it's that one, basically. So they mix. Now you have atomic orbitals, like in the hydrogen atom, but you can put them together, they can mix, they can make two new orbitals. And that's what's happening here. This is the formamidinium or the cesium. So this is the monocation that does not play a role in the orbitals, in the band gap. So here we have the s orbital of the lead and the p orbital of the iodo. So that makes up this valence band maximum. The conduction band minimum is mainly the 6p of the lead. So that's this one here, and the 5s of the iodo. So you see that, okay, especially the anti-bonding character of the HOMO, that is very, very special. Okay, some people say these perovskites, they are lousy materials. You just put salt, you put them in the solution, you spin coat them. You don't need, like for silicon, this perfect crystal that you need to saw, that you need to dope. So it's very, in a way, it's very simple, but the properties are extremely good. As a semiconductor, they work as good as silicon. And that is really amazing because efficiencies and these properties, they are influenced by recombination. In a solar cell, we want to use light. We want to make charges, a plus charge and a minus charge. And we want them to diffuse to the electrodes, but they can also recombine. The plus meets the minus and they annihilate, they kill each other. So that we call recombination. Band-to-band radiative recombinations. If these charges meet, they can emit a photon and then the ground state is formed again. You can also have trap-assisted recombination that's depicted here. So if there's a state in the band gap, then charges can be lost to that state and they are dissipated, they are lost. Recombination is key to a good material. This is a literature thesis of Rosa and describes all these aspects in more depth on recombination in these materials. And recombination is somehow correlated to defects and these band states. So here we have such a lattice. We have all these octahedra of the perovskite. They are nicely connected. We have a lot of them, but we have a vacancy. This here is a lead vacancy. So you see that there should be a lead atom, but it's not there. So this is a defect. This here is a defect of the A cation, so like the formamidinium. This here is a defect of the halogen. So if you have a crystal and just an atom is missing, and this can happen, then you have a defect, so you can lose charges there. We can also have interstitial. So this is just that an atom is accidentally within the lattice. It shouldn't be there, but it somehow ended up there. So it is also a defect. It is something you don't want. And so here there's a lead ion, basically attached to the lattice, or a halogen atom attached to the lattice. There's a third type of defect, and that is an anti-side. Lead and the halogen, they've switched places. And this is not something that I've just invented. If you look at this literature, then people have found these types of defects. And of course, in every material, so silicon is of course made out of these ingots, the crystallized silicon that is actually crystallized from gaseous silicon compounds. It is a crystal because the crystal is like perfect and it has no atoms that shouldn't be there. It has no defects. So that's why defects play a role in every solar cell material or in any semiconductor. We have these kinds of defects. And now the defects, they have an energy. They're like extra state. In normal semiconductors, like gallium arsenide, these defects are trap states, and they are mainly within the band gap. So you have the band gap, the valence band, the conduction band. So in between, there's these defect states. And so charges are lost there. Now for the perovskites, because of this anti-bonding character of the maximum, these trap states, they are lower in energy. So they don't matter, they don't play a role. They will not influence the efficiency a lot. For silicon or gallium arsenide, the traps are within the band gap, within this energy difference. For the perovskites, they are basically in the bands. So they are more close to the orbitals out of which the band gap is composed. So they are lower in energy. So the HOMO, it is not influenced by these defect states. So in this way, you can correlate the defects and the orbitals or the states. Defects and orbitals, it is in a way very chemical because you're looking at the orbitals of a semiconductor material and it is correlated to the properties. Now, as I told you, this is basically on infinite crystals, periodic boundary conditions. Stress been trying to do DFT on these kinds of materials. He actually gets, this is a finite material. So you see that the orbitals are similar. They also have this anti-bonding character. But the funny thing is that in his calculations, the LUMO is centered on the formamidinium ions. These are some of the sources that I use, so some of the papers. I can also recommend a very colorful PhD thesis on perovskite nanocrystals, very nice. So the last picture we discussed actually is also from the thesis. And so this gives you some more information on the structure and the electronic properties of these perovskites. A question from Mirte. Recombination is something you absolutely don't want in dye-sensitized solar cells. I don't quite understand why it is so important for the functioning of the perovskite solar cells. Could you explain? Recombination is something you never want. So charge recombination in a device, it means that you're losing charges. This represents, in a simple way, the functioning of such a solar cell. Here you absorb light, then one of the charges moves this way, and the other charge moves that way. Now, if this one, if it recombines here, then you lose it. So charge recombination, it is a loss channel, always in silicon, but also in perovskite, also in dye-sensitized solar cell. You want to avoid charge recombination, especially through defects. There's one thing that I recently learned over the last few years, and that is radiative recombination. So that is not losing charges through trap states. The HOMO and the LUMO, you have the valence band, the conduction band. Light creates charges. These charges, you want them to move around. But if they can go nowhere, if they cannot go to an electrode, then they keep wandering around. And you want them to wander around until they find each other again and emit light. That is what we call radiative charge recombination. It means that if you create charges in a solar cell and they cannot form a circuit, they do not go into an electronic circuit, then you want the material to be such that these charges will find each other and emit light. It means that you can test it yourself if you have night goggles or a near-infrared viewer, or maybe something, take a filter out of your iPhone. But if you take a solar cell and you connect it to a power source, if you put a current through, then light comes off the solar cell, but it is light with the energy of the band gap. So you can measure it. You can measure it with a fluorimeter. It's easy. I did it myself. It takes you an hour. But so if this is very efficient, that means that you don't have this. So that you don't have trap states where the charges are lost through other processes. If they're not in a circuit, if they're not part of a working solar cell, but if they're an open solar cell, then it is ideal if only this happens. Radiative charge recombination, this emission of light, and that's actually, so that's in the Shockley-Kleiser limit. So there's a theoretical limit of solar cell performance, and this process, it is in there. It's unavoidable. You cannot avoid it. You want it to be the only thing happening if you're not connecting the electronic circuits. For me, it's also counterintuitive because I'm used that fluorescence is a local property of a chromophore, and you want to quench the emission by electron transfer. That is what I did in my PhD. But if you look at a semiconductor, if you have a solar cell, but you're not making current with it, but you're just shining a light on it, and the electrons cannot go anywhere, they will be lost somehow. So if there are dark trap states, then the electrons will go through these states and get lost, get dissipated. But if they cannot do that, then they can only emit light. So the ideal solar cell, if you put it in a light-emitting diode configuration, then it has like an extremely high efficiency, 100% efficiency of light emission. That is the ideal solar cell. And for gallium arsenide, that works like a charm. So if you take a gallium arsenide solar cell, which has like 28% efficiency, if you put a current through it, then basically a large amount of the charges you inject are generating emission in the band gap. It was very surprising that the perovskites became so big in the solar cell field. Nobody basically expected that. The anti-bonding character of the valence band, that is an extremely, a relatively important factor. Well, it's also, well, I find it quite surprising. And this is the explanation that comes from Nature Materials review. And this is what I can tell you, that it is basically the level of this antibonding orbital that is higher than normal relative to the trap states. The trap states are below, so they don't play a big role. If they are in between, then it is known that they have a big effect.